But if for whatever reason I can't get YouTube to okay lectures on abstract interpretation, which admittedly is kind of a horrifying topic for at least some people, I will find a way to record it and distribute the video otherwise. But I was really hoping for this live stream thing to be, easier. Okay, well, we are again live on YouTube. So to answer I guess it's time to start. It is in fact a little past time to start. Welcome all to the second online lecture for this class. As you have now noticed, we are doing all of the lectures over Zoom. So you've all joined. The lectures are also being live streamed over YouTube. So those are available for you to rewatch later. I'm not taking attendance. If for whatever reason you cannot make this time because of childcare or elderly care, or because you or someone you know is sick, please feel free to watch the videos later and stay up to date with class that way. Just a reminder, the way to ask questions during video lectures, if you click the participants button, it'll usually be in the top of the screen toward the middle. You will see a list of all the participants, and in the bottom of that panel, you will see a button called raise hand. So if you raise your hand, I'll call on you to ask questions the same way we do this in class. So just to practice, why don't you all click raise hand now, and then you can lower the hand afterward. All right, great, cool. So we still, we remember how to do that. That's good. I'm just gonna do that reminder probably at least 1 or 2 more times, just because, make sure that you all remember how to ask questions. Otherwise, this will be even more isolating and lonely than it already is. So last time we talked about this kind of interesting, different approach toward dealing with analysis of large programs. We basically identified this problem, which is that the weakest precondition mechanism we've been using up until now, that allows you to write general purpose arbitrary specifications, but that also means the analysis is slow, it's difficult to scale, and a significant problem, which is just that it's hard to write those specifications. So we introduced this idea of having simplified conditions that we use to describe the results of programs. And one example we took is non-negativity. It's pretty easy to identify which variables in your program ought to be non-negative. And then there are some simple rules that capture how non-negativity propagates through expressions and across statements. So we introduced methods of doing that for all sorts of statements, including for loops. And for loops, we had this 2 sort of components come together to make that possible. One is we leverage this idea of a merge operator or an OR operator on our simplified conditions. And then we also had this idea of executing a loop, refining our understanding, as in broadening our understanding of what the values of different variables might be until the result of the analysis stops changing. And finally, we talked about how to generalize this from the basic idea of non-negativity to this broader idea of just, you have some kind of set of conditions that you want to state about about values or program states in the program. And there we ended up defining the structure called the lattice, where that lattice structure involves that OR function. And we talked about how to turn that lattice into an analysis that you can run on programs. So what I want to now talk about is some common ways an analysis like this might be instantiated. Non-negativity, despite its simplicity, is not a particularly useful or important analysis. But today I'll talk about some common domains, some common ways in which this framework called abstract interpretation is used to analyze programs. And in particular, we're going to talk about first a complete description, what it means to define one of these analyses. And I'll in particular focus on this idea of defining the conditions, the merge function, and then defining transfer functions and refinements. And not only how do you define them, but what does it mean for those definitions to be correct, to be valid. Then we'll look at determining possible ranges of integer values using intervals. And that's going to introduce this interesting quirk of an infinite height lattice. So we'll talk about how to deal with that. And then finally, we'll talk about inequalities. And that's going to introduce this idea of relational lattices. And again, we'll talk about how we can incorporate that into our work. So I'm going to start by going back to basics. So what is one of these task-specific analyses? Well, it begins with this idea of having a set of conditions for the variables and the program states in the program. So for each of those conditions, you might have some set of them, and each condition C that corresponds to some property of a variable or a value or a program state. I'm going to call that condition P sub C of X. So I want to show you this as a mathematical definition, but also give you a sense of how you might implement this as a program. So I'm going to now switch from the slides to an implementation of the same idea in Daphne. And I'm going to start here with defining the conditions. So here I'm looking at that analysis for non-negativity that we've mentioned a few times here. And in that case, the valid conditions are that a variable is either non-negative or it is of unknown sign. And each of those conditions corresponds to a predicate, a property of integers. So if the condition is non-negativity, then it corresponds to that integer being non-negative. Otherwise, it just corresponds to the true condition. If we say that an integer has unknown sign, then that is always true of any, that could always be true of any integer. So now that we've defined the set of conditions, we want to go ahead and implement that lattice structure. And when I say lattice structure, remember that what I mean is we need some kind of merge function for conditions. In other words, we need something that approximates an OR for conditions. So in particular, if you have two conditions, C1 and C2, then you want to write down a condition that is weaker than either of them, implied by both of them. And actually, now that I think about it, this is backwards. I got to change this stuff now because people might be rewatching this. That is weaker than either of the two conditions independently. So that merge function that defines that, we're going to use that when we talk about loops and when we talk about conditionals, because when you have a conditional, your program does one of two things. And so the program state ends up in one or two different states. And then we need to merge those two states somehow to describe the result after taking one or the other branch. And then finally, to make this whole analysis useful, you have to learn interesting conditions at some point in the program. And those are defined by what we call transfer functions. So what a transfer function does is it is the analog to some function you might execute in your code. So if you have some function f in your code, you execute it on some argument x, then what you want to know, if you have some function f, oh man, for some reason I can't write on it anymore, weird. If you have some function f and some argument x, and you know that x has condition C1, then the transfer function should give you a condition of the output of that function. Okay, so let's look at what those look like specifically for non-negativity. For non-negativity, we have this set of conditions for variables and states. And I'm going to call those two conditions NN and unknown, so non-negativity and unknown. And each of those, as you've seen, corresponds to a property, either that the property of some integer x, either that x is non-negative or the true property, which basically means we know nothing about x. And the merge function for conditions, well, we have two conditions. It's a binary function, so we can write down that merge function as this table. And each cell in that table, that corresponds to some property we have to prove. So for example, this cell here, where the first argument is unknown and the second argument is non-negativity, that corresponds to the condition where the first argument is unknown, meaning that it's true, The second argument is non-negative. So now we know that X is either unknown or X is non-negative. Well, true or something is always true. So the result of this left-hand side is just true. And that's also what this right-hand side is. And that establishes that we've defined this merge function correctly, at least in this cell of the table. And then finally, transfer functions. Well, the transfer function, we're going to define one for any functions that we want to have special support for in our analysis. So for non-negativity, one of the functions you might be interested in is addition. So with addition, if you add two non-negative numbers, you know that the result is non-negative. Whereas if you add a number of unknown sign to a non-negative number, you don't know the sign of the result because you could add like -5 to 2. So this is our sort of definition of a non-negativity analysis. And I'm going to pause here for any questions anyone has about this set of three things we use to define an analysis: the conditions, the merge function, and the transfer functions. Go ahead, Matthew.
So, and these are all defined over some specific domain. All of the conditions, merge functions, and transfer functions relate to some domain that these predicates are applied to.
Yeah. So what you're asking is, here non-negativity and question mark, I've written them down as if they're predicates over integers.
Okay.
It sort of depends on how you want to apply this, which is part of why I've been sort of sweeping it under the rug. If your language already has a type system, then perhaps your analysis is only going to run over values of certain types. On the other hand, if your language does not have a type system, then you have just one type of values, then presumably, the way you think about it is unknown means anything that's not an integer, or an integer if we don't know that it's not negative.
Okay, thank you.
Yeah, you can think of a type system as actually being an analysis of this type, where the set of conditions is one per type in your program, and the merge function is effectively throw an error, because if something is an integer or a double, that can't happen, or whatever the case may be. And the transfer functions being the type definitions for the type declarations for each function. But if you already have a type system, and probably you already have a type system in your language, then you can maybe apply this to only certain types in your program. Any other questions? Okay, so let's look at implementing this as an actual program. I've already shown you our definitions of the non-negative and unknown condition, and the definition of what each condition means for an integer argument. Now let's look at the merge function. The merge function, remember, has to be weaker than either of the input arguments. So here I've defined a function called merge. It takes as arguments two conditions and returns a condition. And its post condition, the requirement for that merge function to be correct, is that for any input, if it satisfies one of the two input conditions, the or of the two input conditions should imply the output condition. So that's the requirement that I've written down here, and that's exactly the correctness requirement for merge functions. And then the implementation here is just translating the table you saw into an if statement. So there's only one cell in that table that returns anything but unknown. And so I've implemented that by testing for that one table cell and returning that value. Matthew, your question?
This might be a slight diversion, so you can answer it later. But here we have a quantifier for all x. And yep. Last time we were using quantifiers in Daphne, it was relating to over arrays. So how is, I don't know, is it still able to perform verification over the entire, like all integers, I guess?
It is able to perform a verification. And the way you think about this is that, remember that actually deep down, this isn't just for all x, this is really for all C1, C2. because we're still testing it over all input variables C1 and C2. So here, yes, we have a for all. That's actually fine because there's still no quantifier alternation. And then when we negate this one big for all, we get an existential and it'll solve it correctly. So in some sense, we get this, we kind of get this for free. And existential here would probably, well, it wouldn't work, but it wouldn't say, it would be more difficult for it to solve. More broadly, Z3 has a bunch of techniques to try to solve quantifier problems, even if you can't always succeed. At some level, all these quantifier tricks mostly boil down to guess at reasonable values to substitute in for the quantified variables. And if you guess right, you win. And then if you don't guess right, then I guess it just takes a while and you're sad. So,
okay, thanks.
Yeah, I mean, clearly in this case, Daphne handles this without a problem. And anytime you have quantifiers, you start getting, concerns over will that actually go through. But in this case, it happens to be the case that this goes through fine. Okay, so that diversion aside, so here we've defined our merge function for conditions. And note that I'm doing this in Daphne specifically so that I can write down these post conditions and have Daphne check that I did it correctly. But, normally if you're writing a static analysis, you don't necessarily also try to verify it in Daphne. It's just convenient in this case. So that's not sort of a requirement for using this technique, but I wanted to be explicit about this correctness requirement that you need to satisfy. Naturally, if you were just writing this analysis in Java or whatever, you'd have to basically check this in your head or define some tests or something. Okay, so once we define this merge function, we're also going to define some transfer functions. And transfer functions, again, they stand in for the behavior of a program function, but on these abstract conditions. So here I'm defining a transfer function for plus. And the way to think about this is to say, well, plus has two arguments, x and y. And I have conditions C1 and C2 that describe facts about x and y. And so here we have that x satisfies C1 and y satisfies C2. What my transfer function should return is a condition that describes x plus y. So in other words, here I have descriptions of x and y. I want a description of x plus y. And that's why it's called a transfer function. It transfers knowledge that we have about the plus function to knowledge about these abstract conditions. And so my definition here actually happens to be exactly the same as my definition of the merge function. But that's just a funny happenstance of how non-negativity happens to behave. And you can tell that the functions are different because they actually have different specifications. So questions about transfer functions? Okay, and so transfer functions, you in some sense define as many as you want. The more you define, the more functions your analysis will know something about. So for example, you might want to define a transfer function, especially in the non-negativity analysis, for lengths of arrays. And the way it would work is, well, array lengths are an expression like this. And the way we've set it up, we don't actually know anything about arrays. So I'm going to define my array length transfer function to not take any argument at all, because we know it has to be unknown. We never say anything about arrays. And so this should return some condition that summarizes the output of array length. And the specification is going to be similar. Array length has one argument. So we're going to quantify over all arrays. And then we're going to say that, well, we don't know anything about that array. So there's not going to be anything to the left of the implication because there's no conditions coming in. And we're going to want to state that that condition is true of that array. I need to. And in this case, well, we know that all arrays are non-negative in length. So here I've now defined a new transfer function. And this transfer function always tells you that anytime you get the length of some array, you get a non-negative result back. Now, naturally, there's more than one valid way to write a transfer function. I could also return unknown here and just, disclaim any knowledge of array lengths. The result would still be an analysis that gives you correct results, by which I mean results that are true, but it would be less precise. Or another way to think of less precise is to say that that would raise more warnings during the analysis of a program. So questions about this array length thing? Adding new transfer functions, having additional knowledge about functions that are executing in your code. Okay, in that case, let's summarize, let me just summarize how we're going to apply this analysis so we can sort of run through an example. When you have one of these analyses and you want to analyze some function in your code or even a whole program, which you can think of as a function that just has arguments on the command line or whatever. Well, what you're going to do is you're going to first initialize all those parameters, unless you know better, to some unknown condition. And one of your conditions always has to be some kind of unknown that disclaims all knowledge of some value. Then at each step, when you take a step in the program, you're going to have some rule over how do you over approximate the resulting conditions after executing that statement. So you always need to make sure that you over approximate the results so that if the conditions tell you something is impossible, it really is. Now, when you reach a conditional expression, you'll have executed two different sets of statements that might have different results. So to continue going after the conditional ends, you need to merge those two results, merge the conditions at the then and the else branch to get one set of conditions that describe the current program state. And then finally, with loops, you need to repeat the loop because you might not know sort of the loop invariant. So you start by knowing that some input, say, is non-negative, then you execute one step of the loop and you say, well, now I don't know, you need to restart the analysis with this less specific input value. And as long as you have a number of states where it has this property that we call finite height lattice, then you know that eventually all loops will stabilize because there's only so and so many ways you can change the value, the condition that you have analyzed for the variables in the loop. And so just applying this basic strategy, this gives you a fast, scalable analysis that you can apply to pretty big programs. And so here's sort of an example that I want to walk through. This is a shortened version of the binary search loop. And what we're doing here is we are starting by defining the low and high, then we enter a loop, and then we have our conditions that determine which of the two, whether we move the left-hand endpoint or the right-hand endpoint in a binary search. So I just want to fill out this table. Now, on the right here, I have at each statement in the program the conditions that we have for each variable prior to the execution of that line. So I have a variable here for a, which is a value, I have a column here for a, which is a value in our program. But since a is an array throughout the whole execution, it'll actually have the unknown state at all points in time. Then before the execution of low and high, if these are just inputs to our function, we don't know anything about them, and we fill them in with unknown as well, and same for the merge operation. Now, after we execute this first line, low equals 0, we know that the constant 0 is non-negative. We have a transfer function defined for that. In this sense, we're thinking of constants as 0 argument functions. So low is now known to be non-negative, and we can fill that in. But we haven't changed the value of anything else, so those stay the same. Now we enter into the loop. Yep, Matthew?
So do we need to assume we have an infinite number of transfer functions for this? So for each, non-negative constant, or I guess.
Yeah, I mean, obviously, you can think about it that way mathematically, and it might be a little clearer. The way you would actually do this is you'd have some method int const, which would take no arguments, but it would take an integer. And so we think of this int const of 3 as one transfer function.
Okay.
And then its post condition would be something like we have to ensure that for all x, we don't have any conditions on x. X is in some sense a parameter, not an actual argument to this. Just that the condition we return is true of x, and then we would write something like if x greater than or equal to 0, return non-neg, else return unknown.
Okay.
That's pretty interesting. I probably, no. Huh. That's actually quite weird, and I didn't expect that. You know, I'll figure that out later. Sorry. Okay, so I was sort of stepping through the execution of the program. We say that low is initialized to 0, so that tells us that it's non-negative after the first line. Then after the second line, we take the length of some array. Now, the array itself is unknown, but we have a transfer function that the length of any array is always non-negative, so that allows us to learn that high is non-negative as well. And we didn't modify low, so that is still non-negative. Now we enter this loop. So the first statement in this loop is the assignment to m, the expression that computes the average of two values. And the way that we can basically, the way we compute this is we say, well, first of all, 2 is non-negative. We have a transfer function for that. Then low plus high. Well, low and high are themselves non-negative. And then when we add the two, the result is non-negative as well. And then we have this division of a non-negative value, low plus high, and a non-negative value, 2. And so the result of that is also non-negative. And so that assignment teaches us that m is non-negative. And naturally, we haven't modified low or high. So that happens as well. Now let's look at what we've got after executing the two branches. So after executing the low branch, we assign m to low. So that copies the non-negative from here into here. That actually doesn't cause any change. And similarly, here we assign to high from m. So in both of these cases, in the then branch and the else branch, we have the same results, that low, high, and m are all non-negative. So when we union the two together, we don't actually get any changes. And because we don't get any changes, when we re-look at this loop, when we go back to the loop, we see that our assumption, which is that low is non-negative and high is non-negative, hasn't really changed. So we, at this point, we're done analyzing the loop, and we have the results of our analysis. And those results might tell us, for example, that m stays non-negative throughout the whole process. And that might, allow us to know that certain array accesses are fine. So questions about this sort of stepping through of an execution? Go ahead.
So on the last slide, you were talking about over approximating.
Yep.
At each step. What is there an example of that here? I'm not quite clear on what.
There's not an example of that going on here. I mean, in some sense, there's over approximation always going on, because we actually know that 0 is 0, not just some non-negative value. But that's limiting us to just, the fundamental thing is that we're limited to the set of conditions that we could ever state. That's the core, like you could say, problem that's going on here. So instead of knowing that low is exactly equal to 0 and high is exactly equal to the length of a, all this analysis can tell us is that both are non-negative. There's clearly some loss of information going on there, but then from that, given that loss of information, that's our over approximation. Every future step, it's true that in this case, when we do low plus high over 2, we just analyze this on the level of non-negativity. We don't try to figure out what's the highest it can be, what's the lowest it can be, etc. For example, we're not tracking, that it is always less than high, even though that's a true fact. We're ignoring that information. Our analysis has to assume that m might somehow magically end up bigger than either low or high. So that's the kind of over approximation I'm talking about. It all boils down to this idea that we only have so and so many conditions we can state. And if there's something we can't state, it's something our analysis can't learn.
Gotcha. Thank you.
Other questions? Go ahead, Calvin.
Example, in Daphne, you might want to like say some condition at the end of a function, like stating, for example, the non-negativity of a number or something.
Mm-hmm.
I like weakening the kind of like verification you do, like instead of like all these different theories to do like a different approach, or is it like too intertwined with like the different like that'd be like a bad idea?
Well, so we'll see next time, which I guess is in a week. We'll talk about sort of a real world implementation of this, which is called, a thing called the checker framework, which is used in, a lot of companies like Amazon, for example, is a big user. And what you'll see there is that you can annotate both the results of functions and the arguments to functions in terms of the conditions you expect to be true of them. So you can write down, this is a function that I promised returns a non-negative number, and then the analysis will actually check that and issue a warning. And then, that warning is actually the same system that it applies to, for example, if you, have an array and you take an index and that you want to know that that index is non-negative, otherwise you issue a warning. Okay, so far we've defined an analysis. We saw that this analysis basically involves a set of conditions, a merge function, and as many transfer functions as you kind of feel willing to write down and you feel are important for understanding your code. Now I want to raise an interesting issue that comes up when you define an analysis this way. And it's best illustrated with an example. So suppose you've got a program with an if statement. Well, that if statement has some kind of condition. So this, for example, is a piece of code that might be used to do Python style variable access, array indexing, right? So in Python, if you give a negative index to an array, you mean that you count from the back. And that means that to implement that, you're going to test if the index you give is bigger than or equal to 0. And if so, index from the array, otherwise don't index from the array. Well, imagine what our analysis would do if it were to analyze this method. It'd start by saying that I has unknown sign. Then it would analyze the then and the else branch. And when it analyzed the then branch, it would notice that a sub I could potentially be an invalid index because I having unknown sign might be negative. Now, in fact, that's not true. We're guarding against that with the if statement. So this brings up this notion of flow sensitivity, whereby flow sensitivity, I mean the control flow of the program tells us something about the values in the program. So in particular, if the control flow is such that we reach this array index, then because of the conditions we executed along the way, we now know the variable I to be non-negative. So how do we implement that kind of thing? How do we make our analysis smart enough that it could, yes, whoever put that in chat, you are correct. Okay, so how do we add this kind of knowledge to our analysis? Well, the standard way to do this is using something that we call refinement functions. And a refinement function is basically kind of like a backwards transfer function, specifically for Booleans. So what I'm calling a refinement function appears here, and we define one of these for every conditional kind of expression, which I've written down here as R, but unfortunately as T later. Man, really sad. And what this refinement function does, it has to propagate information backwards. We start the refinement function knowing that the comparison we tried to do, or the conditional that we tried to execute, was true. And of course, we have some information about the arguments of that conditional that are produced by our analysis. What we want to do is produce new refined conditionals to describe those arguments now that we've done the conditional and learned that it was true. So for example, if you have the expression I is bigger than or equal to 0, then you have a non-negative value greater than or equal to, sorry, you have an unknown value greater than or equal to a non-negative value. And you know that this is true. Well, if something is bigger than a non-negative value, it must itself be non-negative. So we want to take this information that this is true and propagate this backwards to learn that in fact this left-hand argument should have been or can be refined to non-negative. And then that non-negative, that applies to the variable I. So now we know that I is non-negative, and we can add that to our program state and now use that later on when we do the array access. So that's sort of the example, that's sort of the general approach. Let me show you how that works for the specific case of non-negativity. So I'll go back to Daphne here, past all of my transfer functions, and now I've got a refinement function for comparisons. And specifically, I'm looking at the greater than or equal to comparison. So here's how I've set up my refinement functions. I'm calling the refinement function compare true. And specifically what I mean is it's for comparisons, greater than or equal to specifically, that return true. And you can see somewhat later down on the screen, I have a compare false that basically is for comparisons that we know return false. And compare true starts with two conditions, C1 and C2, that describe the arguments X and Y of the comparison. So what I've got here is I've got C1 describing X, C2 describing Y, and also the conditional return true. So we know that X is greater than or equal to Y. What the refinement function returns is two new conditions, which I'm calling C1 prime and C2 prime. And they're just, in some sense, better versions of C1 and C2. And you can see that I must have the output that C1 prime describes X and C2 prime describes Y. So one way that you can always implement a refinement is to leave both conditionals unchanged. But in this case, we can add some special knowledge about comparisons that helps our analysis. And in particular, what we're looking at is if the second argument to the comparison, Y, is known to be non-negative, and X is bigger than or equal to Y, then we know that X must be non-negative as well. And so I've added that bit of smarts to the analysis right here. And you can do the same thing, in effect, in reverse. So here I have the same thing with compare false. And you can see that between these two methods, I've got the same arguments and the same results, but in the specification, in compare false, I know that the comparison returned false, whereas in the compare true, I know that the comparison returned true. And as a result, here the logic is a little bit different. If I know that X1 was non-negative and it wasn't bigger than or equal to Y, then that means Y must be strictly greater than X, and that means that Y itself must be non-negative. So questions about these refinement functions that I've implemented? Go ahead.
Yes, I have a question. I'm not sure why these are different from the transfer functions, at least like conceptually.
Yeah, I mean, the conceptual difference that I described is you sort of work backwards. So here, the X plus Y is, we're describing the output of X plus Y. Here, we're consuming the output of X plus Y. We already know that X plus Y returned false. And we're using that to reason backwards about the arguments.
I see, thank you.
So the way that I've described refinement functions here, I've specifically described them for Booleans. And that's because, the control flow of a program is defined by Booleans. And generally speaking, the things your analysis will learn as it goes are specifically Booleans. You aren't necessarily going to learn midway through the program that X actually has to be 2 right here. But you can learn that at some point in the program, this condition must have returned true. In principle, you can define these sort of backwards transfer functions, these refinement functions, for things like addition as well, because you can see that now I've learned a new thing about my argument x, but what if x itself was the sum of two things? Maybe I want to learn something additional from that. Implementing those kinds of refinement functions is relatively rare because they are kind of rarely useful, but in principle, you could do that as well. So basically, we've got transfer functions that work forward. You know something about the arguments. You want to learn something about the results. And you've got refinement functions that work backwards. You know something about the result, like that the result is the Boolean true, and you work backwards from that to the arguments. Other questions? Okay. So here we've got that same refinement function, but described in tabular form. Effectively, I'm looking at what happens when the conditional greater than or equal to returns true. And what you're seeing is that in all cases, the results are the same as the inputs, except here, if an unknown value is bigger than a non-negative value, what I'm learning is that that unknown value is actually non-negative all along. And so usually you have these, and I'm not showing it here, but I showed you in the Daphne code, you'll have the same for not greater than or equal to. So flow sensitivity, this is our first sort of refinement that I wanted to add to this idea of having a task-specific analysis that tells you something about the results of your program. So, okay, that's idea number one. We've defined this general notion of an analysis with, a set of conditions and a merge function and some transfer functions. And then we added this additional refinement of refinement functions that let us learn something from the control flow of the program. And now I'd like to move on from that to add an additional tweak to this general idea. I wanted to work through that. Okay, to give you another tweak to this idea, and we'll talk about this idea of finite height versus infinite height lattices next. So before I do that, any questions about this idea of flow sensitivity? Okay, great. So let's take a different sort of thing that we might want to know about integers. So far, we've talked about non-negativity. And as I sort of said in an aside, non-negativity is actually kind of an uninteresting fact to know about integers. It's it's rarely a useful fact or an easy fact to learn. But here's something that you might want to know instead. What you might want to do is something stronger than non-negativity, which is you might want to track ranges for integer variables. And that comes up a lot. One place you see this is if you have, like a fake enumeration, right? Like you have an integer, but it has to have a value from 1 to 5 because, 1 stands for, on, and 2 stands for waiting, and 3 stands for timeout, etc. Another case that you want this, of course, is array bounds checking, though that's a little more complicated. We'll see that as we keep going through the lecture. And in general, some kind of interval analysis is sort of a classic analysis for programs. You'll find that your compiler does this internally as well to do certain optimizations. So for example, if it knows that a value cannot overflow, perhaps it can do something useful with that information. So we're talking about ranges for integers. Well, one reasonable place to start is, what kind of ranges are there? You might say that a range is 2 integers and describes the set of all values that lie between them, let's say inclusively on both sides. But as I mentioned, you're going to want to start by having sort of unknowns. And so you're probably also going to want to have ranges of the form negative infinity to b a to infinity, or negative infinity to infinity, which I'm just writing as a question. So this is if you had some mathematical integers. Naturally, if you have 32-bit integers or 64-bit integers, then this inclusive range is good enough because there is a smallest value and there is a biggest value. And then if we have this set of conditions, we're also going to want to define some merge functions, and that's pretty easy because if you have 2 intervals that overlap, like this interval and this interval, their union just takes the left-hand endpoint of the left-hand interval and the right-hand endpoint of the right-hand interval. And so we can compute that by minning the two left endpoints and maxing the two right endpoints. And then once we have this kind of definition of intervals, now we can talk about transfer functions and refinements. So transfer functions for a constant are pretty easy. That's a 1-point interval. For addition, that's actually not correct. It's a plus c and b plus d, because addition is in some sense a monotonic function. And then some functions are not monotonic. So like negation, for example, applied to a single value, that's going to flip your interval, because you think of if you have an interval like this and this is 0, then when you negate it, you get an interval like this. And so from a to b, negative b to negative a. And finally, you can even learn some interesting things from comparisons when you do interval arithmetic. So what this expression is telling you is that suppose you had two values, x and y, and maybe the intervals look like this. So here you have y and here you have x. Well, if x is less than or equal to y, then x definitely has to be less than the biggest possible value y can hold. And that means that for x, we want to take this right-hand endpoint and move it to be the right-hand endpoint of y, if that's smaller. And so that is what the min right here is doing. It's saying that the right-hand endpoint of x is the smaller of the right-hand endpoints of b and d. And similarly, we're doing the same for y. So questions about what we've done here to define an interval analysis. Okay, and naturally we could define this analysis not just in slideware, but we could do it in code. So here I have a definition of intervals. They are similar to the definition you saw on the slide. So we have finite intervals. We have intervals where the left-hand endpoint is infinity, where the right-hand endpoint is infinity, and then the unknown interval. And these correspond to the conditions you would expect. So a finite interval, that's an inclusive interval on both sides. Whereas if you have, say, the right hand is infinity, then you only need to check the left-hand endpoint. And then when we define things like the merge function and so on, it's a little bit hairy, but the basic idea is that we take the min and the max of the two endpoints when we do the merge. The hairiness that comes out here is just due to the fact that we're treating infinities as separate from integers, and so my implementation is to track which of those endpoints will actually be defined and fit this in correctly. But you can see that the specification is still identical to what you saw before. If C1 describes X or C2 describes X, C must describe X. And then we can do the same to define it for addition. So here I've got the transfer function for addition. I know that C1 describes X, C2 describes Y. I must describe X plus Y. And we do that by adding the left-hand endpoints and adding the right-hand endpoints. So questions so far about our definition of intervals? Okay, in that case, let's just step through and apply this. Here I've got a small little program that uses the pop count method, which tracks the 1 bits of an integer. And I'm using that to describe what that integer is. So the first thing we do is we set output to a constant, and that actually allows us to learn that the length of the output, which here I'm tracking separately, is an interval from 3 to 3. Now, when we apply the pop count method, let's say that X is a 32-bit integer, we know that there can be at most 32 bits that are on. So the spec of pop count tells us that even if we don't know anything about X, we know that I is between 0 and 32. And of course, we know that the length of the output hasn't changed. And then when we reach a conditional, like here, that's going to allow us to make use of that refinement function. So if I is greater than or equal to the length of the output, that means that I is at least 3. So after executing this code, we know that I is between 3 and 32. And then after executing this line of code, we know that I is actually the length of the output minus 1. So that's going to be 3, 3 minus 1, 1. So 2, 2. Now you don't see it here, but this if statement actually has an else branch. There's just an else branch that doesn't do anything. And in this else branch, we get to apply our refinement function as well. So in the else branch, we know that I is less than the length of the output. And since the output is exactly 3 long, that means that I has to be somewhere between, well, it was always bigger than or equal to 0, but now we know that it's less than 3. So it has to be between 0 and 2. And this means that when we merge these two cases, the then and the else case, we will end up knowing that I is between 0 and 2. And that will actually allow us to verify that this array access is valid. So questions about this little step through of applying our interval analysis? Okay, great. Well, there's a problem with the interval analysis we've defined so far. And it goes back to the structure of the lattice that we've defined and this property that I call infinite height. So I've drawn the lattice here. At the bottom, you have one of the conditions. There's obviously a much bigger lattice involved here, but this is just one of the conditions, which is the condition on x that x is between 0 and 0, namely that it's exactly 0. And that is more specific than the condition 0, 1, namely that x is either 0 or 1, which is less specific in turn than the condition that x is 0, 1, or 2, which is in turn less than 0, 1, 2, or 3, and so on and so on. And you can see that we can actually continue building this lattice infinitely high, each time getting a new interval that can describe the results. Well, this kind of infinite height structure can lead to a problem when we're analyzing programs. And specifically, this creates a problem for analyzing loops. So here's one example of that. I've defined value I. It starts at 0. And so initially, it has the interval 0, 0. And now I'm going to run a loop with some complicated condition that is hard to analyze, where we're just going to increment I. In other words, we're just counting up until some condition is true. Well, to do that, we're going to start by knowing that I is 0, 0. We're going to analyze the body of the loop, I++, and at the end of that, learn that I is between 1 and 1. Now, we need to combine the two results of that to get a new starting assumption for the loop. So now our assumption isn't that I is exactly 0, it could be 0 or it could be 1 when we enter the loop body. We analyze the loop body, we know that at the end it's 1, 2. We union the results. Now we know that I is between 0 and 2 at the start of the loop. And as you can see, we can keep repeating this whole analysis over and over again, each time getting a wider interval and each time getting a different interval, which means that our analysis will continue because we repeat our analysis of loops until our analysis stabilizes. So there's clearly going to be some kind of problem. And we want to find a way to solve it because if you can't analyze programs with loops, you basically can't analyze programs. And by the way, the same general kind of problem might come up depending on how you set it up with recursive functions. So one idea is simply that we're going to ignore all ranges of all intervals that are too long. So if your range a comma b is only valid when the gap between them is less than 1,000, then eventually your analysis of loops, you'll keep repeating things iteration by iteration, but eventually that interval will be too wide and you will end the whole analysis. So here, we're going to do a couple of iterations of the analysis, and then at some point, we're going to know that I is between 0 and 999. Then one step, then one iteration of the loop will result in I between 1 and 1,000, and when we apply OR, we no longer have the option of saying 0 to 1,000 because that interval is invalid. And so we just have to give a wider interval, namely 0 to infinity. And then actually when we apply this loop body to 0 to infinity, we get the same result. I is still between 0 and infinity. And so now we finally stabilize the iteration of our loop. So this is a good technique. It ensures that we can always analyze all of the loops. And naturally, you now have a knob to tweak. If you really need to, you can analyze loops for more than 1,000 iterations, but you probably don't want to. And for most loops, this sort of limitation will work fine. Yeah, Calvin?
So for here, could you also just define this like 0 to infinity to be like the upper join like way that like unknown is, and they like serve the same purpose?
Yeah, so I mean, what you've got here is you've got a lattice that's like you've got 0, 0, and then you've got 0, 1, and then you got a bunch of iterations, and like I got 0, 9, 9, 9, and then above that is 0 to infinity. And this isn't actually the unknown value, because this is still more specific than -1 to infinity, which is still more specific than -2 to infinity. And at the top of that list is finally, oh, -infinity to infinity. So it's not that we've replaced the unknown value. The unknown value could definitely be substituted in, but we could also do something more specific. And basically the upshot here is that, well, you might have a loop there, you know, both sides expand at the same time, and you might need to do this trick of replacing an infinitely long lattice with some large but finitely long one multiple times. So your goal is, what we've basically done here is we've modified the lattice so that this infinitely long path no longer exists. And you'll want to do this sort of trick until all of your paths are of finite length. So this might be one of your rules, and your other rule might be that, say, a comma infinity only valid if a is, you know, bigger than -1,000. Then that might be another property that you want to enforce, and that would stop you from, you know, going up this infinite chain without end. Does that answer your question? I'm not totally sure. I said something that helped.
No. Thank you.
Okay. Other questions? Okay. So this general strategy of sort of changing our lattice to not have this infinite height property, that totally works. It has one downside, which is that when you're not in a loop, there are now, you know, things that you want to say and can't. So, you know, you might have a variable that you happen to know is between, you know, 1,000 and 3,000, and that's an important sort of fact about your program. Variable's not involved in a loop anywhere, and yet if you make this change, you're going to lose that information. You're not going to be able to state the property, and that means that when you over approximate, then you're going to lose information that you wanted to keep. So the trick that people actually apply is a slight twist to this. You want to ban ranges that are too wide, but only when you're inside a loop. So this is a pretty interesting idea, and what we call this idea is we say that we have two different lattices. We have a wide lattice for inside loops and a narrow lattice for outside of loops. And effectively, we apply what we call widening and narrowing operators to go between them. So the widening operator takes you from the outside of loop state to the inside of loop state. And you can also think about this as being widening because it takes an interval and makes it wider. Your widening operator might take 0, 1,000 and turn it into 0, infinity. Your narrowing operator, you know, if we think of these as two different lattices, goes backwards, but often what going backwards means is just keeping the same exact interval. So that's that's one way that you could that's how you set up this idea of having an inside of loops, outside of loops working in different ways. And this allows you to fix that infinite height problem while not hurting the results of your analysis when you're not inside a loop. Questions about this general idea? Okay, and so then the way that you apply this, right, is that if you have a loop in your program. Then you have some property that's true here. You have some condition that you know. You're going to take that condition here, execute the body of the loop. You have some new condition C prime. And then before feeding it back into this process, you want to take C prime and widen it so that the actual OR that you do in this loop back to the beginning of the loop and reanalyze, that OR happens in the wide lattice. And so another way that some people think about widening operators is instead of having two lattices you transfer between, you think of it as a sort of a looser OR operator, and some people define it that way. But the way I prefer to think about it is having two lattices that you move between, and one lattice is specifically used just for this loop issue. So any questions about widening and narrowing? Okay, cool. So this was our sort of second interesting twist or interesting improvement to this idea of a task-specific analysis. And then the third one that I want to talk about is this idea of relational conditions. So my example of this will be, suppose you want to track which variable in a program is the biggest one. You want to track inequalities between integer variables. In this case, this range analysis that we've done is not enough, because in our range analysis, we've treated each variable independently. So for example, suppose you have a valid variable x and you don't know anything about it. Then when you do x minus 1, you still don't know anything about the results, but you should know that the result is smaller than x. So what we want is a different kind of domain. Ranges don't work, intervals don't work, that can track this kind of information. And what we call these are relational conditions. Relational conditions are called that because they have the form of a relation. Namely, they take multiple variables as arguments. So if a normal relation, like non-negativity, that takes a single integer and tells you something about it, namely that it is non-negative, a relational condition takes multiple variables and tells you something about the combination of them. So for example, that one is less than the other. So relational lattices work fairly similarly to ordinary lattices, but there are a few tweaks that you need to handle more carefully. And by the way, apologies for all of the code samples not animating correctly. I'm not really sure what happened with that. So when we're defining a relational analysis, we need to be a little more careful because a relational analysis involves multiple variables. So you need to make sure to update it at the correct time. So for example, if you assign to one of the variables involved in your relational condition, like here we're assigning to y, you need to make sure to remove the fact that you knew about the old value of y in the conditional. So here you want to know nothing at all about the ordering of x and y, unless you have some other information about x and y on the side. And in particular, you're also going to have to be careful when you do any kind of merges. So here I'm doing a merge where the two sides of my statement had orderings x less than y less than z and y less than z less than w. And remember that these are the things that we know on either branch of a conditional, a then and the else branch, for example. So we want to combine the two together and only know the stuff that's true in both cases. And that's going to be this y is less than z. So we need to make sure to filter out any conditionals, any relational conditions that might be invalidated by either branch of the condition. And you can see that this can sometimes be tricky. So for example, when we're talking about inequalities, we basically have a condition that might be true for any pair of variables. So in some sense, you want to be careful not to define too general a family of conditions, because then there might be too many of them to track and it might be too complicated and you're back to this problem that your analysis is very general but very slow. But you know, conditions, for example, it's usually not the case that you have interesting inequality facts about all the variables in your program. So inequality analysis, for example, is one that's relatively cheap because it's usually only involves a couple of variables at a time. So questions about how I've defined this idea of a relational analysis. Okay, great. Well, in that case, let me introduce sort of the most common way that this sort of relational analysis is actually used. And this is a set of conditions that we call octagons. The reason we call them octagons is due to their shape. So an octagon represents a set of possible x and y values, which takes the geometric form of an octagon where each side of the octagon is at a 45-degree angle. So one way to think about that is geometrically, we've got these octagons, and that's good for slideware. But the other way to think about it is as a range of values for each variable. So that's the top and the bottom bar of this octagon. And then also a range of values for the sum and difference of the octagon. So you can see that, oh, actually, this is x minus y. That along these lines, x minus y is fixed. And so we have a range of values for x. That's the left and the right sides. We've got a range of values for y. That's the top and the bottom sides. And we've got ranges of values for x plus y and x minus y. And that defines our octagon. So when we have one of these octagons, it actually turns out to be pretty easy to do unions and merges on them. So for example, if we have these two octagons, well, we can work out the possible range of x values. We can work, sorry, y values. We can work out the range of possible x values, and those we think of as just two intervals that we handle independently. And then the x plus y and the x minus y, well, those are also ranges that we can write down. So here's our range for x plus y, x minus y values, and then our range for x plus y values. And so by combining those together, we get the joined octagon that combines both of them. And so this is how you can define a merge function. And this, if you think about an octagon as intervals for x, y, x plus y, and x minus y, then you can see how you can derive that merge function pretty efficiently. Questions about octagons? Well, in that case, we've got this definition of intervals. There's generally speaking, when you implement this, there's a few things you have to be careful of. So in particular, if you have bounds on x and y, then you also have bounds on x plus y and x minus y. But as long as you implement, but it's not too difficult to implement these correctly. And this is also an analysis that tends to be relatively quick. And then the reason you want to do an analysis like this is that it allows you to handle common idioms where you add and subtract certain values. So for example, the sort of inequality you'll often want to track is whether a variable is less than the length of some array. Well, that on its own is useful, but idioms where you take an index and you add one to it are fairly common. So it's actually useful to know that I minus a dot length is not just bigger than 0, but it's actually bigger than 1, which allows you to do this array index while knowing that the indexing is valid. And then you can also define refinement functions on these sorts of you can define useful refinement functions on octagons pretty nicely, because anytime you have a comparison of two values, that's actually going to turn into a sum or a difference of those two values and a bound on that result. So refinement functions for these octagons are also fairly simple, and that allows you to do an analysis where you do things like treat the 0 case specially, or the length minus 1 case specially, and then do something with your array. And then in particular, a place that tracking things with octagons makes a lot of sense is when we're talking about array indexing. And you may have noticed that I've been using this as a running example throughout this whole section on abstract interpretation. When we're talking about array indexing, there's all sorts of different properties that we end up wanting to track to analyze realistic programs. So first, you're going to want ranges on the integer variables. You're going to want to know that an integer is less than the length of some array. You're going to want to know that certain arrays are the same length. And then you've got all sorts of like our weird little programmer idioms. So you might have a value that is exactly equal to the length of the array and use that to represent a subsequence of the array. The index of operator in a lot of languages that can return -1. So you want to handle that separately. In Java, the binary search operator actually returns the correct index or the negation of the correct index, which is pretty fun to tell you whether or not it actually found the value or is just telling you where it would go if it were in the array. And so you can imagine that if you just sat down to write down conditions for each of these cases, you'd have a lot of different complicated conditions that are in play. And actually, we'll see an example of sort of a lot of complicated conditions when we look at the checker framework. But another way to represent the same analysis is to think about this as just octagons on the array lengths and all the integers. So ranges on the integer variables, well, that's the part of the octagon that isn't relational, that just talks about X or Y. Integers being less than array lengths, well, that's why we've got array lengths and integer variables. So we can talk about a bound on X minus Y as telling us that, if a.length minus I is bigger than 0, then we know that I is less than the length of the array. Same length arrays. Similarly, we have two array lengths, and we know that the difference between them is exactly 0. And then when we talk about these things that are off by 1 or even negations, you can add that to the octagon pretty reasonably. So when you do the 1 past the end of the array, well, that's just the difference between I and the array length not being bigger than 0, but being bigger than or equal to 0. Same with index of. And when you have these negative indices, you aren't talking a.length minus I is bigger than 0. You're saying a.length plus I is bigger than 0. So with octagons, we can sort of handle all of these different things that come up in reasoning about array bounds, but we talk about them through one data structure instead of through 6 different ones. So questions about octagons or array bounds, checking and how we might use them. Okay, so I've used octagons here and inequalities as a way to demonstrate relational analyses, but there's actually lots of relations that are common to track in this sort of analysis. You might want to know that a dictionary or a map has a certain key, that a string matches a regex. You might even want to have a relation between certain pointers in the program and locks that tells you when you're allowed to access them. And when we talk in a week about the checker framework, I'll show you examples of all of these different analyses being used to tell you interesting things about the program. So even though I introduced this this whole section as telling you that we're now going to look at not a general purpose verification, but task specific verification, you can see that there's actually a lot of different tasks that we can handle in a task specific way, all the way down to ensuring that our concurrent programs work correctly. Something that might actually be fairly difficult to set up using the traditional Hoare logic verification. And you saw a little bit of that in James Wilcox's talk. So what we've seen today are basically 3 ways of taking this idea of task-specific analysis and improving it, refining it, making it useful in a lot of everyday sort of verification tasks. So laid out a complete description. In that description, we added this idea of refinements to allow us to reason about control flow. Then we introduced this idea of infinite height lattices and widening and narrowing operators that allow us to deal with them. So that's allows us to do this much richer range of analyses like ranges for integers. And then we talked about relational lattices. So lattices that tell us about the relationship between 2 different values and how we can use that to track order, to track array bounds, and all sorts of other useful conditions in our program. So hopefully that's given you an overview both of the theory and a few examples of the practice of building one of these task-specific analyses. And I keep telling you this is a thing that actual programmers use every day, and so that's what we'll be focusing on next time. Apologies for the slide. It turns out that black text doesn't work on starry background. But what we'll be looking at is a tool called the checker framework. The checker framework is a framework for defining these task-specific analyses for general purpose Java programs. So what I'll do tomorrow, in a week on Tuesday is I will be I'll be first using a couple of these analyses, show you how they apply to Java programs, allow us to tell interesting properties, and then more broadly showing you how to define an interesting analysis. We'll use a pretty simple one to allow us to do our own analysis of programs, and I'll talk a little bit about different industrial uses of that capability. So that's what is for next time. Before then, on Thursday, you have your Milestone 2 presentations. Remember that for the Milestone 2 presentation, just to guard against internet issues, I am asking you to upload a recording of yourself giving your Milestone 2 presentation. Those should be pretty short. If you are struggling to figure out how to record yourself, voice and slides, or however you want to do it, or demo if you want to, please reach out to Manasij or to me, and we'll try to help you set that up. So we've looked into how to do that on various operating systems. Remember that you have the same time limit as you had before, 4 minutes or 8 minutes, depending on solo or group project. And the other thing I'm asking you to do is fill out the course feedback. Since you are all on your computer right now, you can go do that immediately by just opening up Canvas. So that would probably be a good idea to do before leaving this this session. And other than that, you're free to go, and I'll take any questions anyone else still had. Yeah, go ahead.
Yeah, about the recording of the presentations. Do you know about any software on Mac?
Yeah, so on Mac, the Mac comes with this thing called QuickTime Player. And if you open up QuickTime Player, you will see a new screen recording option. So when you do new screen recording, you've got to do some stuff to allow it to do that. I guess I haven't done a screen recording on my new Mac yet. But you can set up a screen recording there, and you can also have it record your voice over your laptop microphone or over a headset if you have one of those.
Okay, thanks.
Any other questions? Okay, Manasij, it's just you and me, so that is all.